commitment to creating inclusive and impact-oriented AI solutions. With over 16 years of teaching experience and more than 20 research publications, Dr. Lavanya has made remarkable contributions to the academic and research community. Her insights into modern AI technologies, especially in the field of NLP and transformer models, continue to inspire both students and researchers alike. We are truly privileged to have her with us today, and we look forward to gaining valuable knowledge and inspiration from her session. Please join me in warmly welcoming Dr. Lavanya. Over to you, ma'am. No, ma'am, we can't hear you.
Just a minute.
Now we can hear you, ma'am.
Yeah, 1 minute. Now, can you hear me?
Yes, ma'am, it's audible.
Okay, fine. Is the PPT visible, ma'am?
Yes, ma'am.
Yeah. Okay. So today I'm going to discuss about recent advances in CNN for image analysis. So the agenda of today's session will be, I'll be just giving you the recap on CNN fundamentals, and then I'll explore on more on the modern CNN architectures. Then I'll give you a small introduction to vision transformer models, and I'll show you a demo on bone fracture image classification using the custom CNN model and other modern CNN architectures. So this is going to be the agenda of today's session. Hope in the previous sessions you would have gone through the CNN fundamentals. Can someone tell me how many of you are so familiar with CNN? You can send me messages through chat. How many of you are familiar with CNN? Please respond. Yes, okay. Okay, so for the people who are new to CNN, I'll just give you an overview on CNN, convolution neural network. Convolution neural network is the architecture which performs well in image classification task and image segmentation, image, so many tasks with respect to image image classification, right? So there are 3 layers in CNN: convolution layer, pooling layer, and fully connected layer. Okay, let me discuss how these layers works first, and then we will go and discuss about the advances in CNN architectures, modern CNN architectures. Okay, so the first layer in a convolution neural network is convolution layer, and the second layer is going to be pooling layer. Finally, you will have a fully connected layer, from which you can do any of the tasks like image classification or object detection, and whatever you want you can do after the fully connected layer, right? So convolution layer, this is the core layer of convolution neural network. It performs convolution operation. What it does is, suppose you are given with the input image. The image is, let us consider here you have a input image matrix, which is 5x5 of size. And what we are going to do is, we are going to take a filter or kernel, and we are going to convolve that filter over the input matrix, image matrix, in order to produce the feature map. That is what we are going to do. Okay, so here the filters in CNN model, the filters are going to have certain weights. You can see here there is a 3x3 kernel, and which is having certain weightage for each and every cell. Okay, so based on the kernel you have chosen, you will be able to extract the particular feature map. That is the concept. Okay, so you will be moving this kernel over the input image. That is, you will be taking considering the stride size. Okay, how many strides you are going to perform over the input pixel matrix. Based on that, the movement of kernel will be done on the input matrix, image input matrix. So after doing the strides of the filter over the input matrix, you will be able to come up with the feature map. Okay, next you'll be having pooling layer. The purpose of pooling layer is, it is going to reduce the size of your feature map. That is the purpose of the pooling layer. Okay, so from the previous layer, we have got a feature map, and on top of the feature map, you are going to apply pooling filter. Okay, so based on the size of the filter, you will get a reduced feature map. What's the purpose of doing the pooling is, you are going to reduce the size of the feature map. Also, while performing pooling operation, you will be able to uh, improve the shift and noise invariance in case of multiple images. What do you mean by shift and noise invariance? Okay, so I might take a feature. Say, for example, I'm going to predict fracture in a bone. Okay, so in my input image, the fracture might be present in the one image. The fracture might be present in the center of the image, whereas in other image, the fracture might be present in the corner of the image. Okay, so wherever the bone fracture is there, using pooling layer, you will be able to extract the features, that is the fracture features with respect to bone fracture, exactly based on the pooling layer, right? Okay, so that is what is the pooling layer is able to improve the shift and noise invariance, whatever noise is present in the image. So that will be neglected, and you will be able to extract the necessary features from the given input image. So that is the advantage of pooling layer. So basically, it performs compression of your feature map. Okay, that is reducing the feature map size. And also, while it is reducing the feature map size, it is able to improve the shift and noise invariance. You can perform multiple types of pooling, like average pooling, max pooling. Generally, people will be performing average pooling, and in some cases people might be interested in performing max pooling operation. Okay, so in this layer, the model is not going to learn any weight. Okay, so that you are supposed to take into account. Only in convolution layer, weights will be learned, but in pooling layer, no weights will be learned. Okay, so this is a simple convolution neural network. First, you had a convolution layer. Okay, then you had a pooling layer where you can perform either max pooling or average pooling. After performing pooling operation, you will be getting a feature map. This feature map will be flattened, and that will be given as input. So that will be given as input to a fully connected layer. Okay, in this fully connected layer, you can use a multi-layer perceptron, and on top of it, you can do any kind of classification. So generally in convolution neural network, there are 3 layers: convolution layer, pooling layer, and fully connected layer. The first 2 layers are meant for feature learning. Okay, and the second layer, fully connected layer, is meant for classification task. Right? Okay, so this shows you how the CNN is able to learn hierarchical features from the given input image. Hierarchical features in the sense, you'll be in a convolution neural network, you will be having many convolution layers followed by pooling layers, and then you will be having convolution layer followed by pooling layer. Likewise, you can have n number of layers, and then finally you can have a fully connected layer to flatten the feature maps, features you have extracted, and then finally you can perform any classification task. Okay, so what is the purpose of having layers? In deep convolution neural networks, each and every layer will be extracting different features. Say, for example, the base layer will be extracting edges, the corners, and the textures, like that. The next layers will be learning in more detail the features, and the final layer will be learning the exact features which is required for your classification task. Say, for example, I have taken an image where the convolution neural network is going to classify the images into dogs and cats, like that. Okay, so here you can see we have used 3 layers, convolution layer. And the first layer, it is learning the basic features, and the second layer, it is learning textures, colors, like that. And then the final layer, it is able to learn the parts, subparts of the given image, and it is able to learn the complete object. Okay, so this is how the CNN, convolution neural network architecture, is being built. So you will be having n number of layers. Each and every layer will be learning different features. Okay, that is what is hierarchical features. Layer 1 will learn the basic features, and the next layer will be learn the higher features than the basic features. Likewise, you can have n number of layers which will be learning the features in detail. That is what, how the depth, how much deep your network is, those many fine details your network will be able to learn. Okay, so evolution of convolution neural network architectures. You can see here, LeNet was the first LeNet 5 was the first convolution neural network layer which was introduced, and it is used in handwritten classification of handwritten digits task. Okay, in 2012, AlexNet was introduced. AlexNet, VGGNet, GoogleNet, ResNet, all these architectures were introduced for ImageNet, ImageNet data set classification competitions. So many competitions are held yearly, and in during that competitions, people came up with different architectures which performed well for that image net classification, ImageNet data set. So AlexNet, VGGNet, GoogleNet, ResNet, DenseNet, MobileNet, and ConvNeXt, or all these architectures are different architectures which were introduced. So let us discuss the architectures one by one. LeNet 5. LeNet 5 was the first architecture which is based on a convolution neural network. Okay, so the purpose of this architecture is for handwritten digit recognition. The data set which was used for that is MNIST data set. Okay, so the architecture of this LeNet CNN is it had 7 layers, alternate convolution and pooling layer. Finally, you had a fully connected layer. So here they have used TANH activation function, and average pooling was used. In pooling layers, average pooling was used. Okay, this was a small network which was introduced first, and this network learned less than 1 million parameters. Okay, the input image which is given for this LeNet with respect to handwritten digit recognition task is 32 cross 32 grayscale image. Okay, so this is the architecture of LeNet. Okay, so here you can see convolution layer. You had initially convolution layers, then you had pooling layers. Okay, next convolution layer, then pooling layer. Finally, you had 2 fully connected layers. And then on top of it, since it is a 10 classification task, 10 neurons at the final layer, which is able to classify the handwritten character into any one of the 10 classes. So this is the architecture, and it had less than 1 million parameters. It learned the parameters of this model is less than 1 million parameter. Next comes AlexNet. Okay, so AlexNet is a little deeper CNN architecture with the activation functions. Here they have used this ReLU activation functions, and they have used dropout. Dropout concept was introduced at that time, and people started using and ReLU activation function also was introduced at that time. So instead of TANH activation function, people have started using ReLU activation function, and dropouts. Certain layers were dropped in order to reduce the number of parameters which is being learned for the same ImageNet classification task. Here, this AlexNet architecture had 5 convolution layer and 3 fully connected layer. Okay, so here the filter size is 11 cross 11, and the stride is their stride size is 4. Okay, instead of using stride size as 2 or 1, here they have used stride size as 4 to perform aggressive reduction in the feature mapping. Okay, so that is the idea, and they have replaced TANH activation function by ReLU activation function, and they have dropped out certain layers, certain neurons in the fully connected layers. They had 3 fully connected layers. They have used dropout concept in the final layer, which is meant for reducing the overfitting of the data set. And they have introduced data augmentation techniques also here in this layer, and the model was that model, AlexNet model, was trained on 2 GPUs. So the number of parameters it has learned is 27.55 million parameters. So this is the architecture of AlexNet. Okay, so this performed well in case of ImageNet classification task when compared to the previous model. Next comes ZFNet. Okay, so this is based on AlexNet architecture only, but the concept here they have introduced is, instead of having a large filter size 11 cross 11. They have reduced the filter size as 7 cross 7, and they were able to see that when we are reducing the filter size, they were able to capture good low level features. So that is the inference they have got by introducing this architecture. The stride size they have used is 2 instead of 4. So in the previous architecture, they have used stride size as 4, but here they have used stride size as 2. So these are the minor changes they have made in the previous architecture, ResNet, and they have come up with ZFNet. Okay, so the key innovations in this architecture is they are able to visualize what the convolution layers has learned. What are the basic features the layers were able to learn? So when they applied small filters, 7 cross 7 filters instead of 11 cross 11 filter, they were able to preserve the basic features very well when compared to the previous architecture, AlexNet. So that is the inference they have got by introducing this architecture. So you can see here the difference in total number of parameters between the AlexNet and ZFNet is 1.45 million parameters. Next, they have introduced VGGNet. So this is the first very deep convolution neural network which was used for image recognition task. Okay, so here they had there are two variations of VGGNet. One architecture had 16 layers, another architecture had 19 layers, VGG16 or VGG19. So this was the first deep convolution neural network architecture that was introduced. And here it used 3 cross 3 convolution, which is stacked sequentially one after the other. Okay, so how many parameters the model has learned is 138 million parameters, a huge number of parameters when compared to the previous architecture. Since the this particular neural network architecture is a very deep architecture, it had 16 layers or 19 layers. Because of that, we had the model was supposed to learn more than 138 million parameters. Okay, but the model performed well for the image recognition task. So what they have inferred after introducing this architecture is how many layers we are going to add in depth, that is going to give more accuracy in the classification task. And similarly, instead of applying huge filters, they were applying small filters, say for example 3 cross 3 filters instead of 11 cross 11 or 7 cross 7 filters. Here they have applied 3 cross 3 filters, stacking one on top of the other, so which was able to extract more spatial features in depth when compared to the previous architectures. That was the success of VGGNet architecture. So here, from this architecture, you will be able to perform transfer learning. It means that this particular architecture is trained on huge dataset, ImageNet dataset. So if you want to perform a classification task for your images, say for example, you have some medical images with you as input, what you can do is you can take this VGGNet architecture. Okay, then you can fine tune this model for your data set. Fine tuning is nothing but freezing the first few convolution layers of this VGG architecture. That means you are not going to change the parameters, model parameters, which are learned in the basic layers of your VGGNet. Basic features, say for example edges, everything, those basic features which were learned from the ImageNet data set, that will be freezed, and rest of the layers you can unfreeze and you can train the VGGNet architecture with your medical image data set. This task you call it as fine tuning. Okay, so this was the first architecture. This is called as transfer learning also. Okay, so you have trained the model in some data set, a huge volume of data set. The model has learned the features already. So if you want that learned features to be applied for your application, then you can do so by unfreezing only the few layers and then training the VGGNet on top of your medical image data set. That is called as fine-tuning task. This is called as transfer learning also. So when you are doing that, you are saving the training time. Also, the model will be able to easily learn the higher level features, since it has already learned the base features already. So it will be able to learn the higher level features, and you can apply that for your classification or any task easily. So this is the first architecture which paved the base for transfer learning with respect to image processing, VGGNet. So this is the architecture of VGGNet. As I already told you, the kernel size, filter size is 3x3 throughout the architecture. Okay, so the number of parameters learned is more than 138 million parameters. So you can see here, you alternate convolution layers and max pooling layers are there, and finally you have fully connected layers followed by a softmax layer for classification. Okay, so the next architecture which was introduced is Google LeNet. Okay, so this is the this is the winner of 2014 ImageNet large scale visual recognition challenge. Okay, so what is new about this architecture is as the convolution neural networks go deeper and deeper from LXNet to VGGNet, the number of parameters the model is supposed to learn started exploding. Okay, so when the VGGNet had nearly 138 million parameters that has to be learned, the training of such massive models required huge computational power and huge storage. So in order to overcome that difficulty, they came up with a idea that is called the key idea behind the Google LeNet is inception module. What is this inception module? Instead of using sequentially the convolution layers, parallelly they are applying convolution layers, and they are concatenating the output of those convolution layers, and that is given as input to the next pooling layer. So that is the kind of introduction, new idea they came up with respect to Google LeNet. Okay, the inception module, introduction of inception module. So what they are doing here is they are using different filter size. Instead of using that in sequence, they have used that in parallel, and they have concatenated the output of all the convolution layers, and that is given as input to the pooling layer. Okay, so when they did this in parallel, they were able to reduce the dimension, that is, reduce the number of parameters that are being learned. Okay, depth wise, they were applying 1x1 convolution filter. Okay, in that case, they were able to bring down the number of parameters minimally when compared to the previous architecture. Okay. And they have the other concept which was introduced here in Google DenseNet is global average pooling. Okay, so they replaced the fully connected layers using global average pooling, and that fully connected layer learned only fewer parameters when compared to the previous architecture. So this is the architecture of Google DenseNet. You can see here, initially the input image is given, and you are having convolution layer, max pool layer, and you can see there are inception modules which are between the max pooling layers. So this inception module is the one which is performing different convolution in parallel, and all those convolutions outputs are concatenated, and that is given as input to the next layer, which is nothing but your max pooling layer. By doing so, they were able to reduce the number of parameters. So that is the achievement that was done by Google DenseNet. And here comes the ResNet architecture, residual connections. It is called as the residual network. This is the winner of 2015 ImageNet classification task, this model. Okay, so in ResNet, we have many variations of ResNet based on the number of layers. Okay, so what is the motivation of ResNet architecture is when we go deeper and deeper, you can see starting from AlexNet, the number of layers were kept on increasing, and the number of parameters which need to be learned in case of each and every model kept on increasing. Okay, so Google DenseNet came up with an idea of reducing the number of learned parameters. Still, the model depth was kept on increasing. So the problem is when the model depth was kept on increasing, people faced vanishing gradient problem and optimization difficulties. Okay, so to overcome these two difficulties, ResNet was introduced, residual network. So the idea behind ResNet is skip the connections between the different layers. Instead of direct mappings, residual mappings between the layers was carried out, using which they were able to reduce the number of parameters that needs to be learned, and also they were able to achieve the optimization. Say, for example, they prevented the vanishing gradient problem. Okay, next, they were able to keep the low-level features which are being learned by the base convolution layers intact. Okay, they were performing residual connections only in the higher layers. By doing so, they were able to reduce the number of parameters that has to be learned, and also when we are having a data set which is very small, all this deep convolution neural network architecture started facing overfitting problem. So in order to overcome that, also they come up with this idea, residual connections. Okay, so this is the architecture of ResNet 34. Okay, it had 34 layer. Okay, you can see here residual connections are being done in between the layers, between the next convolution layers, instead of having the straight connection. So this by doing so, they were able to reduce the vanishing gradient problem. Also, they were able to keep intact the low-level features which are being learned by the model, so that can be used for transfer learning in case of new data set. Next, So we have seen so many architectures, CNN-based deep neural network architectures, which were used for image classification task. And each and every architecture came up with new idea, solving different problems which were faced by the convolution neural network architectures. So what are the new advances that are being done in and rest of the CNN architectures are they played with kernel sizes and the convolution layers, depth-wise convolution layers. And then instead of using a supervised model, they used a self-supervised model. They were giving only the image as input, and the model was able to learn whatever the features that were present in the image, so that while using self-supervised model, the base model can be used to perform any kind of task with respect to image classification or image recognition or image segmentation. Any kind of task can be carried out on top of the self-supervised models. So next, they have introduced transformer CNN based transformer models also, and explainable CNN models. These are some of the recent advances of CNN model. So now I'm going to discuss about vision transformers. Before moving into the topic, may I know how many of you are aware of transformer models and architecture of transformer models? Please let me know. How many of you are aware of transformer models? Just heard about it. Okay. Others, please. How many of you have worked with transformer models for text? And how many of you have worked with transformer models with respect to image? Just heard. Okay. Not worked. Okay. So, see, till now I was discussing the differences in architecture, right? I saw in the session details of your FDP program. Initially, they have started with machine learning and then deep learning. So you should know the difference between machine learning and deep learning. Probably then only whatever I have discussed, that you will be able to understand, right? So I'll tell you just what's the difference in machine learning, deep learning, and transformer model. Okay, so in machine learning model, we were extracting the features from the images, and those features were given as input to the classification machine learning algorithms for performing any kind of task for image segmentation or image classification, like that. Okay, in case of deep learning models, the models learn the features on their own because we were giving the image, say for example with respect to classification task, we were giving the image as well as the class labels for all those images. So, and when these two things are given as input to a deep neural network architecture, the architecture is having many layers. Say for example, our convolution, normal convolution neural network architecture, where we had a convolution layer, next pooling layer, and then we had fully connected layer for performing the classification task. In convolution neural network, what it is doing, each convolution layer is learning a feature on its own. For image, suppose for say face recognition task. Okay, so in order to recognize the face of a person, okay, we are supposed to know the features with respect respect to eyes, nose, ears, everything, right? The forehead of that particular person, the chin area, like that. We are supposed to learn different features of a particular person in order to identify that this image belongs to this particular person. So these are called as features. Okay, so each and every convolution layer will be learning the basic features. First, it will be learning the edges, right? All those basic features which it will learn, and then in the next layer it might learn textures. Okay, and then in the next layer it will learn as I told, different subparts of that particular phase. Okay, so those features will be learned in the next layer, and in the final layer the model will be able to combine all the features that it has learned, and it will be able to understand the image of a particular person. That's how the model is able to recognize each and every person. We are training the model, so the model learns on its own the basic features. Different convolution layers learns different features on its own. We are not extracting any features, and we are not giving that as input to your deep architectures. Okay, the architectures are trying to learn the features on its own and trying to perform the classification task. So that's where I have discussed so many architectures which are based on CNN. Okay, so basically previously what people did is they were training the CNN architecture for a particular, suppose if you have image classification task where you had cat images, dog images, images of lions, tiger, like that. Okay, which and along with the images, labels are being given, and we are giving that as input to a deep learning model. So the deep learning model starts learning the features of cat, and what makes the difference between cat and dog, and what makes the difference between cat and tiger, like that. It starts learning the features on its own, and it is coming up with the classification. When we are giving the test data set, it is classifying. So we are not able to achieve better accuracy in case of normal deep neural networks. There comes the transfer learning. So where in case of transfer learning, we are not giving the not transfer learning, semi-supervised learning. In case of semi-supervised learning, what we are doing is we are not going to give the labels. We are just going to train the model on a huge volume of data set, different data sets. We will give us input to the model. The model will be trained on different data sets. So the model learns the different features with respect to different images. And once the model has learned the basic things, what we are doing is we are taking that model. On top of it, we can perform any kind of task, say for example image classification task or image segmentation task. Okay, so likewise the models are being trained. So what it means that suppose you take yourself, you'll be if you are being trained with the different subjects, say for example computer networks, operating systems, compiler, design and programming subjects, all those books are given as input to you, and you started learning on yourself. Okay, so you would have learned certain things. Okay, so a compiler, what are the topics will be there in the compiler, and compiler design, and what are the topics with respect to programming. So which are the key points I should remember? All those things you will learn on your own, and then on top of it, whatever question I am going to ask, you'll be able to answer. That is what is semi-supervised learning. We are not going to give any labels for the data. Only data, huge volume of data will be given as input to the deep architectures, and the architectures learn on their own the different features. Okay, so on top of it, we can perform different tasks, like image classification or image segmentation or any kind of task. Okay, so that is what is semi-supervised learning. Okay, that is the basics of your transformer models. Okay, that is the basics of your transformer models. I'm talking about semi-supervised learning. Okay, so previously I talked about transfer learning. In case of transfer learning, what we are doing, I say, for example, see here I am an NLP expert. Okay, I know how the text will be processed by deep architectures, but I am seriously I'm new to image processing, but I know how the deep architectures will work and what kind of input it will take and how it will learn the features. All those things are common to text and image. In such case, if I am trained on NLP, okay, if I am being fine tuned for image classification, okay, then I will be able to perform image classification also. That is what is transfer learning. Okay, common things, basic features I have learned already. Okay, that is the basics of the previous models which we have discussed, starting from just a minute. So I told you transfer learning, VGGNet. VGGNet was the first architecture which was used for transfer learning. Okay, so this model is trained on huge volume of data set, and also the number of layers of that deep convolution neural network is 16 or 19 layers. Okay, when you are having a deep architecture and when you are training that using a large volume of data set, the model will be able to learn the basic features carefully, so that that model can be fine-tuned for see, this is trained on normal images, animal images or some other images. I am using, when I fine-tuning VGGNet for medical images, okay, so since it has learned the basic features with respect to text. Now, since I am an NLP expert, I have learned everything in case of text. So when I am being slide, I will be easily able to whatever I want, the questions I am supposed to answer, I'll be able to answer because I know the basic details very well. Okay, so this shares the basics between the natural language processing and text, right? Okay, so that is what is the basics of your transfer learning. Okay, so now I'm going to explain vision transformers. In the base of transformer models is self-supervised learning. Okay, self-supervised learning. We are going to give huge volume of data set. The model is going to learn on its own. Okay, and then it is going to perform the task whatever you want to want that model to perform, say for example classification or segmentation task. Okay, the core idea of vision transformer is here we are not using convolution layers. Okay, you can go and see what is the architecture of a transformer model. Okay, you'll be having encoder module and decoder module. Okay, so what is there in encoder module? There will be several layers of fully connected layers. Okay, so and using those fully connected layers, you'll be training the model on top of huge volume of data set. The number of layers will be huge and the model will be learning a huge volume of parameters. Okay, so that the model has learned the data set properly. Okay, when I am giving any task, that model will be able to perform the task easily. Okay, so that is the idea. Okay, here in case of vision transformer, the image is treated as a sequence of patches. Okay. So here the image is treated as sequence of patches. The entire image, input image, will be divided into so many patches, and will be applying. And on top of it, we'll be doing these kind of processing. What we are doing, see, first the image is divided into fixed size patches. Okay, and for each patch you'll be converting that patch into a vector. Okay, like our image matrix here, instead of entire image matrix, we are dividing the image into so many patches, and for each patch you'll be having a flattened vector. Okay, that will be given as input to the next layer, which is nothing but your linear embedding layer. Here each layer will be projected into an embedding space. Okay, so that is nothing but grouping. What you are going to see, and I want to tell you I'll tell you what is the difference between CNN architecture, deep CNN architecture, and vision transformer models. Okay, so that will be projected in the embedding space. So for clustering, it means that you will be able to group pixels which are representing the same feature. Okay, so that will be done in that particular layer. And the next layer is position encoding. Okay, so we should know in a particular image where, say for example, in an image we have clouds, and we have road, and we have trees, we have car. All those things are present in an image. Okay, I should tell my architecture where the clouds were present, either in the top of the image or at the bottom of the image, where the cloud is present. Similarly, where the trees were present, we should be able to tell this detail to the architecture. For that, we will be using position encoding. Okay, so since the transformer do not have the spatial structure, okay, which is nearby, that should be given as input to the model using this layer, which is nothing but position encoding. Okay, after performing position encoding, this sequence of embeddings will be passed through self-attention layer. Self-attention is the base of transformer. Okay, so whenever you type transformer, you will get self-attention. That is the first concept in case of transformers. This is common for the natural language processor transformer models also, vision transformer models also. Okay, what do you mean by self attention? Each pixel tries to find what is the relation between the adjacent other pixels in that particular image. Okay, for one pixel I'll be calculating attention weight with respect to all the other pixel in the particular image. So that is called as self attention. It calculates the self attention on its own. Okay, so now it will be able to correlate which are all the features which are related to each other in that particular image. After doing all these things, so now the model has learned that particular image completely. Okay, so first what we are doing, we are taking an image and we are dividing that into patches, and that is given as input. And patches, for each patch you'll be having a vector that is given as input to the embedding space, where you will be using different embeddings in order to project that in the embedding space. Okay, after that you'll be having positional encoding. Purpose of positional encoding is where that particular feature was present in that input image. So that has to be given as input to the transformer model through position encoding. All these things are embedded, and that is given as input to the self-attention layer, where it is able to find the relationship between one pixel will be able to find the relationship between rest of the pixels in the image. That's how it is able to relate itself with the rest of the pixels in the image. So the transformer has learned the image completely. Okay, so once it has learned the image completely, on top of it, we can perform you can add a linear classification layer, and you can classify, you can make use of those features which are learned by that encoder. Okay, in transformer you have encoder module. So these are the layers which are present in the encoder model. Okay, so on top of encoder you can add a linear classification layer, so using which you can classify the image as classify the image. Okay, so generally you are giving all type of images as input to your transformer model. The model will learn the image completely on its own. Then when you are adding a linear classification layer on top of it, you'll be able to classify that particular image into different classes. That is the idea. Okay, so what is the difference between CNN and vision transformers? Okay, you can see here, CNN basically they work on local features in an image. Okay, whereas in case of vision transformers, they work on global features. As I told you, it is able to understand the image globally. Okay, so in an image I told you, so you have clouds at the top and trees at the bottom, and there is a car in the left corner. So all those things will be learnt globally, not locally, right? Locally in the sense, your CNN will not be correlating the relationship between different features which are present in a particular image with respect to vision transformer. So vision transformers does that very well when compared to a normal CNN, deep CNN architectures. Whatever we have discussed till now, even ResNet was not able to compete with the vision transformers. But ResNet, they are keep on coming with new versions of ResNet with different layers and different new concepts which are being introduced in different layers. In that case, you can compare the performance of the recently introduced ResNet architecture with vision transformers to know the difference, how the images are being processed between these two different architectures. So that's the first point. Feature extraction is basically local feature extraction with respect to CNN architectures, whereas in case of vision transformer, it's all global features. Okay, next. So as I told you, since the vision transformers learns the relationship between each and every pixel based on self-attention layers. Okay, so here the bias will be very less. Whereas if you are comparing with the CNN model, it will be a little high when compared to normal vision models. Okay, and the major difference comes here. In case of CNN, moderate size of data set is enough to train a deep CNN architecture, whereas in case of vision transformer models, you need very high, huge volume of data in order to train a vision transformer model. Okay, so how you can interpret in the sense, you can see what are the features that are being learned by different layers in the vision transformers using attention heat maps. Here in CNN also, we are having different visualization mechanisms using which you can see what are the features which are learned by the convolution layer 1 and convolution layer 2, all those things. Okay, so attention maps show you better details about the features that are being learned by your vision transformer models. So this is the difference between CNN and vision transformers. Now we can see the application of vision transformers in different image analysis. Okay, all the medical domains, people are using mostly vision transformers. In certain cases, even your ResNet architectures will perform better. We need to check which architecture, which layers, and based on the layers and what are the concepts which are used in different ResNet architectures. Based on that, we can see which performs very well. Mostly, the vision transformers performs good in case of your medical domain. Okay, radiologist, they are using VIT and DIT transformers. The task is to classify the chest x-ray images in case of COVID detection data set. People are using these transformers. These transformers are performing better when compared to your previous CNN deep architectures. Similarly, pathologists, they are using to classify the cancer cells into different classes. For that, they are using swim transformer. uh, so likewise, different domain people are using different transformers and vision based transformer models to perform different tasks. Okay, I think you would have attended a multimodal AI session previously, where they would have talked about VLM, vision language model. VLM stands for vision language model. CLIP is an vision language model. Okay, so here in CLIP model, both text and image encoders will be present. Okay, so that will be used to perform the classification task in case of your multimodal AI. Okay, so multimodal AI, VLM stands for vision language model. CLIP, medclip, all these are coming under vision language model, where we combine image and text. Both the encoders will be present in VLM, and we are giving both text description about the image and the text as input, and we are training the transformer models for certain tasks. Those models are performing well when compared to normal vision transformer models. So these are the recent advances in vision transformers, multimodal AI models. Okay, so now I'll show you, I'll just discuss a simple demo of bone fracture classification of using X-ray images. We have applied a custom CNN model, and then all the deep CNN architectures, and we have compared the performance of different architectures on bone fracture classification data set. I'll show you. So in case of medical imaging, we face so many difficulties in processing medical images. There are different types of inputs from the medical domain. Say, for example, X-ray images, CT images, MRI images, histopathology images. Each and every type of image has its own complexity. Okay, so let me say, if you are taking histopathology images, they are very high resolution color images of tissue slides, which is used for cancer grading. Okay, what's the stage of the particular cancer in that particular patient. Okay, so high resolution images are being used. So not all the models you'll be able to process high resolution images easily. The models will be you are supposed to train the model for days together in order to work with histopathology images. Similarly, MRI images has its own characteristics, CT images has its own characteristics, and the X-ray images are basic images. People started working with X-ray images using all your deep convolution architectures, right? So I have taken only an X-ray bone fracture image as input, and I have trained the model, custom CNN model, and other deep CNN architectures, and I'll show you what is the performance of those architectures, right? Okay. So the key challenges with respect to medical images is variability. Okay, what do you mean by variability? When we are taking images, the anatomy of that anatomy differs from patient to patient based on the age, sex, and even based on the body habits. All these are varying. So these things are also has to be taken into account when we are learning features. So this is a key challenge in case of medical imaging. Okay, and also different x-ray we are taking in different from different vendors. Okay, so depending upon the machine accuracy also certain things vary, so that is all going to be the key challenges, right? Okay, even label variability. So when we are working with radiologist, people will disagree between the labels which are given for a particular image. That itself is a big issue. Okay, and also a model which is trained on one hospital data set may not perform well on another hospital data set for the same classification task. So these are some of the key challenges with respect to medical imaging, right? Limited labeled data set, right? And image quality. With respect to image quality also, we are seeking so many problems. All these problems should be addressed when we are dealing with medical images. Okay, so let me show you the bone fracture classification. We have taken data set from Kaggle, X-ray images. Okay, so the data set covers a range of bone fracture classes. So these are different classes which are given in that particular data set. And as I told you, we have used custom CNN, AlexNet, VGGNet, ResNet 50. We trained the model from the scratch, and the other version is ResNet 50 with transfer learning. So we freezed a few layers, a few base layers, and then we fine-tuned the ResNet 50 model for our data set. This model, ResNet 50 with transfer learning, performed well when compared to rest of the models. The data size was 1129 images. So I'll show you. So here we are importing the necessary libraries for performing the classification task. Then what we are doing is we are loading the data set for bone fracture classification. Okay, so we are transforming the image, gray image, into RGB. Then since the data size is very less, okay, all the deep CNN architecture will overfit the model. In order to avoid that, we did different data transformations, like flipping the images, rotating the images, all those things, all those data transformations we did, and we have increased the size of the data set. Okay, so first custom CNN model. Okay, so we have defined a CNN model where we have used convolution layers, then ReLU activation function. Okay, so we have fixed the kernel size as 3 and stride size as 1, no padding. Okay, we have added 4 blocks. Okay, so we have added 5 blocks of convolution layers, and then followed by max pooling layer. Okay, so after doing all those things, we did average pooling. Okay, after doing average pooling, we converted that into a we flattened the new values of vector, flatten the vector, and that is given as input to a linear classification layer, where we have used dropout in the classification layer. So this is the custom CNN we have built. Okay, And next what we did is, with respect to BGG 16, okay, so we freezed everything. Okay, just last layer alone, which is the model is fine-tuned for our data set. We did not train the model from the scratch. Okay, we used the same model which is available with all the parameters. Okay, so BGGNet, AlexNet, both these models, pre-trained models, we have used the same models, just we have fine-tuned for only the last layer is fine-tuned for our data set. We have freezed the previous layers. We didn't do any complete training. Okay, so whereas here, training from the scratch. Okay, ResNet 50 model, what we did is we trained the complete all the layers of ResNet 50 for this particular data set. Okay, so that is one variation, and the next variation is we have freezed till layer 3 whatever weights the model has learned, ResNet 50 model has learned, that we have freezed, and we have unfreezed from layer 4. Okay, from layer 4 we have unfreezed all the layers, and then we fine-tuned the ResNet 50 for our bone fracture data set. Okay, so all the models we have defined, and then training. So this is the training pipeline. Evaluating the models, different models. Visualizing how different models have performed in our data set. So batch size, number of epochs is 20. Learning rate we have fixed. Train and test split is 80 for training and 20% for testing. This is what the training test split we have given for all the models. So you can see there are 10 classes in this particular bone fracture data set. We had 10 classes, and how many image after doing all data transformations, how many images are there in each and every class, that we have listed out here. Okay, in all 10 classes, totally 1129 images were there. The number of classes is 10 classes. Okay, so training samples is 903 and test samples is 226. Okay, so this is training set distribution with respect to different classes. Okay, how many images are taken from each class for training purpose, that we have listed out here. And test distribution also with respect to all the 10 classes, how many images are given as input for test. So that is given here. It's 20 epochs we have trained the model. So our custom CNN, the accuracy is 0.17. Okay, I'll show you here the performance of different models. Okay, so this is the comparison of model performance. ResNet, ResNet 50 using transfer learning, that is performing better when compared to rest of the models. Okay, VGGNet, it is achieving only 0.17 accuracy, AlexNet is 0.13, ResNet 0.26, whereas ResNet, when we are training the ResNet architecture completely on our data set, we have achieved only 0.26 accuracy, whereas when we are freezing the first three layers of convolution layers and then fine tuning the ResNet 50 on our data set, we have achieved an accuracy of 0.46. And custom CNN, it is achieving only 0.15 accuracy. So this is the comparison of model performance with respect to our data set, medical image data set. Since the data set size is very less, we were not able to train fine tune the model properly, and we are not able to achieve the better results. So, and if you are trying to train the model, what will happen, overfitting will happen for custom CNN and all the deep architectures, not custom CNN, the other deep architectures. When we try to run more, train more in more epochs, it tries to overfit because we have less data size with us. Okay, so with this, I conclude my talk. Yeah, if you have any doubts, you can ask me.
Participants, you can post your queries in the chat box, or you can unmute and ask.
Harpreet Kaur have posted a message. Ma'am, can you please share previous slide? Which slide do you want me to share? Types of medical images. Okay. This one, medical imaging. Huh? Yeah. Okay. Okay, so here I am not good at medical imaging side. Okay, I don't know the features of MRI images. I haven't worked. Okay, So in order to show a demo, I have shown you the X-ray images, but I have started working on histopathology images for cancer classification task, where we are finding it very difficult to train the images, because each and every images is having high resolution, and it is taking days together to train a few images. Say for example, for like thousands of images, if I want to train, it is taking 10 days or so. Okay, we are finding it difficult working with histopathology images, and uh, we have worked using VLM vision language model, where the image as well as the description about the histopathology image is given as input. Yeah, Brad's data same. We are also working. We are finding it's difficult to train the model on top of the data set.
Ma'am,
Since we
is
are
it
working, I'm
possible?
not able to share that now.
Ma'am, is it possible to train using Google Colab GPU?
Yes, we are using Collab GPU only.
Okay,
Using that itself, we are finding it difficult to train the model. It is taking so many days.
okay.
Yeah, what is
For free resources, it will be 1 day only, ma'am. Remaining time
yes,
will not.
yes. It gets disconnected for 24 hours only. No, we can stay
Yes,
connected.
ma'am.
Yeah, that is also a problem. Because of that, we are not able to work with such kind of huge volume of data. Is it? We need computing. If you are having computing power on our own, then it will be easy for us to work on such kind of data sets. These are some of the advances in CNN architectures, not vision transformers. Vision transformers are not included here. We have got less accuracy only. Accuracy value is like percentage of accuracy. Okay, 0.17 means 17 percentage. That's it. Yeah, brain data set other than brats, you have many data sets where we were working. There were 7 data sets which were given in journal article. So we started working on 2 data sets. TransMed. Is it a transformer-based architecture? I haven't heard about TransMed. Now, this is my email ID, sklavanya2023@gmail.com. Okay, so the conclusion of my talk is see how we are supposed to learn all this architecture is you should know how CNN works first in detail, and then start learning about deep CNN architectures. For each and every architecture, just learn what are the layers, how many parameters it's learning, and what was the drawback of that particular architecture, which was overcome by the next architecture. Likewise, you can study what is the new technique which is being adapted in each and every deep convolution neural network architectures. And then you are supposed to learn about transfer learning. After transfer learning, there comes self-supervised learning. Okay, self-supervised learning. The transformer models, vision transformer models are coming under self-supervised learning, where we'll be giving only the data set, huge volume of data set, and the model learns different features. From that, you can adapt that model for performing different image, different tasks based on image classification or recognition or segmentation and anything like that. So all those things you can learn, and you can work with small models and try to project what are the features which are learned by that particular model to understand deeper how the base convolution layers learn the basic features which are necessary. Then only you will understand why we are freezing the first few convolution layers when we are adapting the deep architectures for the classification task with respect to our own data set. All those things you will be able to learn.
Thank you, ma'am.
Thank you.
Thank you for your informative session. We greatly appreciate the time and effort you took to share your expertise and experiences with us. On behalf of the organizing team and all participants, I extend our sincere gratitude to you for being with us today and making this session a valuable learning experience. Thank you, ma'am.
Yeah, thank you all. If you want, I can share the presentation with the organizer team, and you can get the presentation also so that you can learn the different architectures, CNN architectures. Thank you. Thank you, ma'am.
Thank you, ma'am. Moving on to the next part of the session, I would like to welcome Dr. Kritika Balakrishnan, who received her BE degree in Electronics and Communication Engineering, an ME degree in VLSI Design, and the PhD degree in Information and Communication Engineering in 2023 from Anna University, Chennai. And during her PhD, her research focused on investigating and analyzing ECG signals using advanced signal processing techniques to classify cardiac arrhythmias. She's currently a full-time postdoctoral research associate at the National Center for Rural Health Professions at the University of Illinois College of Medicine, Rockford. Her research interests include signal processing and the analysis of electronic health records. She's passionate about using artificial intelligence and machine learning to improve healthcare outcomes, particularly in rural areas. Before joining the University of Illinois, she has completed a postdoctoral fellowship at the University of Florida, where she contributed to the Personalized Approach to Improve Liver Transplant Outcomes project. Through the implementation of AI and ML solutions, she seeks to overcome barriers to quality care in underserved communities and improve the efficiency of and effectiveness of rural healthcare delivery. We are happy to have you in our FDP, ma'am. Welcome. Over to you now, ma'am.
Ma'am, I can't share my PPT, ma'am.
Just a minute, ma'am. Ma'am, can you check now?
Yes, ma'am, I'm able to share my screen.
Okay.
Can you all see my screen, ma'am?
Yes, ma'am, you can see.
Yeah. Uh, Thank you for your kind introduction, and thank you everyone for joining this session to hear my talk. Today, I will be talking about transforming organ allocation with artificial intelligence and machine learning, focusing mainly on how AI can improve liver transplantation allocation systems. This AI can help improve liver transplant allocation system. This presentation brings together our work on combining clinical data, ethical frameworks, and advancing machine learning models to make the organ allocation process more accurate, fair, and data driven. Let starts with a brief background on liver transplantation and why it's such a critical area for innovation. In transforming organ allocation with artificial intelligence and machine learning, our focus is specifically on organ allocation for liver transplantation. Now, you might wonder why we choose liver transplantation as our focus. Well, chronic liver disease affects more than 5 million adults in the United States, and many of these patients eventually progress to end stage liver disease. This stage is extremely serious because it involves multiple organ failures, frequent hospitalization, and very high mortality. For these patients, liver transplantation is often the only life saving treatment that can truly improve survival and quality of life. But the entire transplantation process is incredibly complex. It involves not just medical factors but also ethical and logistical ones, like how severe the recipient condition is, the quality of the donor organ, how long it been preserved, and even how fairly the organs are distributed among the patients on the waiting list. At the given time in the US, there are approximately around 13,000 to 15,000 people on the liver transplant waiting list. All of these factors interact in complicated non-linear way, which makes predicting outcomes very difficult using traditional methods. We can even though we have decades of clinical and registry data, it is still challenging to turn the data into accurate, useful predictive models. That is exactly where artificial intelligence and machine learning comes in. These technologies can analyze a vast amount of data. These technologies can analyze large amount of clinical data, laboratory and imaging data together to uncover hidden patterns, helping us predict outcomes such as waitlist mortality, post-transplant survival, or even optimal donor-recipient match. Ultimately, AI and MLs are helping us moving from reactive decision making to more predictive and personalized care. This will support clinicians in making faster, fair, and more data-driven transplantation decisions. Now, let's talk about ethical principles that guide organ allocations. Whenever we think about allocating scarce organs like donor livers, we face difficult ethical decisions. These are three main principles that guide these decisions are urgency, utility, and benefit. First, urgency means that we try to prioritize the sickest patients first, which means the one who are at the high risk of dying if they don't receive transplantation soon. This is why the MELD score was developed to provide an objective measure of how urgently a patient needs to new liver. We will talk about the MELD in upcoming slides. The second is utility, focusing on maximizing the survival benefit and using resources efficiently. In other words, we want to make sure that organ goes to the patients who is likely to have a good outcome after the transplantation and who will benefit in the most in the long term. The third is benefit. It is about finding balance. It is the idea of achieving the best possible outcome across all the patients, not just for one group. We have to think about fairness, quality of life, and long-term results for the entire population of the people waiting for the transplant. Currently, the organ procurement and transplantation network primarily based on the allocation and urgency. This means that the sickest persons are prioritized first, which is ethically justifiable. But this approach can sometimes leaves gap in utility fairness. For instance, a very sick patient might receive an organ but have a low chance for long-term survival, while another patients who could have lived more years with a transplant might not get one in time. That's why there is a growing interest in using AI and machine learning models to help balance these ethical principles by better predicting which patients will truly benefit more, ensuring both fairness and efficient use of organs. Now, let's talk at the current organ allocation methods, which is based on what we called MELD 3.0 score. MELD stands for Model for End-Stage Liver Disease, and 3.0 is the version number. That is the latest update used to prioritize the patients on the liver transplant waiting list. Essentially, the MELD 3.0 is the urgency-based scoring system. It gives each patient a numerical score between 6 and 40, estimating their risk of death within the next 90 days. If they don't receive the transplantation, the higher the MELD score, the highest the risk, and therefore the higher the patient's priority for receiving the liver. Next, the score is calculated using the combination of lab values such as serum bilirubin, which means liver function, then international normalized ratio we used to call as INR, which reflects the how well the blood is clotting, then serum creatinine, which indicates the kidney function, then sodium, it is an important marker for the fluid balance, And also, they included serum albumin, which represents the malnutrition and liver status. This formula also indicates an adjustment for female patients to address the historical disparities in access to transplantations. Since women often had low creatinine levels that underestimate their disease severity, while the question looks complicated. The main takeaway is MELD 3.0 provides a way to objective rank patients based on how sick they are right now. The UNOS and OPTN, the organization OPTN, those are the organization managing the national transplant list. Use the score to decide the order in which patient receives the available organs. However, there is the important limitations as well. The MEL 3.0 is focuses mainly on the short-term pre-transplant mortality. That is the likelihood of dying patients before receiving the liver. It does not take into the account post-transplant survival or how well the patients might do after surgery. This means it tells us who is sickest today, but not necessarily who will benefit the most in the long run. This one of the key areas where AI and machine learning could add value by helping us build models that consider both pre and post transplant outcomes to make organ allocation more balanced and fair. Now that we have seen MEL 3.0, how that works, let's take a look at some of the key limitations of MEL 3.0. Even though the MEL 3.0 is the biggest big improvements over previous versions, it still has some important gaps and affects fairness and accuracy in organ allocations. First, this course focusing only on urgency. As we all know that, meaning it prioritizes the sickest patient first. This ethically reasonable, but it does not consider how well someone might do after the transplantation. So it tells us who is most likely to die without liver, but now who is most likely to survive long term or make better use of that. Second, the second limitation is what we call as static snapshot model. It relies on a single set of lab values taken at a one time in point, like a bilirubin, iron, or creatinine, sodium, and albumin. But patients' conditions can change rapidly from week to week or even day to day. The current MEL score does not capture the dynamic changes or trends over time. The third limitation is it does not take into the account of comorbidities such as diabetes, cardiovascular disease, or obesity, all of which can strongly influence the liver transplantation outcomes and survival. The two patients might have the same MEL score, but their overall health and recoveries or recovery potential could be very complicated. Then another limitation is that a MEL 3.0 has a limited predictive power for post-transplant outcomes. It does not design to estimate total survival benefits. In other words, it can tell us which patient will gain the most extra year of life for transplantation. It also does not include donor-related factors like organ quality, then preservative time, or donor-recipient compatibility, which also are the critical in determining how successful the transplantation will be. So we also know that they are potential gender and demographic bias, especially because the MEL 3.0 still heavily depends on the serum creatinine, because the women typically have a lower muscle mass and therefore lower creatinine, which can underestimate how sickest they really are. possibly lowering the priority unfairly. Finally, there is an ethical limitation that the current MEL 3.4 framework lacks the true fairness mechanism. It struggled to balance urgency, saving the sickest patients, with overall benefit and long-term outcome is not considered. These limitations highlights why we need smarter and more adaptive models. Now, let's look at the role of machine learning in transplantations. We all know that today we have an enormous amount of healthcare data are being generated every single day through the electronic healthcare records. These records includes lab results, imaging data, medication history, clinical notes, and demographic details. Together, they form a vast and rich source of information that can help us understand the patient's health patterns far beyond what traditional models uh, what traditional models can capture. That machine learnings can take advantage of these large data sets to optimize organ allocation and predict outcomes more accurately. Unlike the current allocation model, which uses only a few static lab values, ML models can integrate ML models can integrate uh, longitudinal lab results and comorbidities and imaging biomarkers and even social or behavioral data. This allows the model to predict both short-term and long-term outcomes such as potential transplant survival, graft function, and risk of complications. Another major strength of ML is ability to identify hidden risk factors that clinicians might not easily see and to enhance fairness in the allocation process. For example, AI can detect patients that suggest certain groups like women or patients with atypical lab values are being under prioritized, and it can help correct and it can help to correct those biases. Finally, AI can be aligned with existing ethical framework for organ allocations. Remember the three key principles we discussed earlier: urgency, utility, and benefit. AI can help balance these by predicting both who needs the organ most urgently and who will benefit the most in the long term. In other words, it it supports ethical decision making by integrating data driven insights with fairness and transparency. So we can conclude overall machine learning offers a promising way to move the current urgency only model to more personalized, predictive, and equitable system for organ transplantations. So, for this area, there are some studies developed to overcome the MELD 3.0 limitations. Now, let's talk about some of the data limitations that currently exist in the AI models for liver transplantations. Even though AI has tremendous potential, its performance depends heavily on the quality and completeness of the data it learns from. Right now, most AI models rely on registry database like UNOS and SRTR in the United States. These are the large national data sets, but they often lack granular patient level details and longitudinal informations, meaning that they don't capture how patients' condition changes over time. Many studies also done utilizing the cross-sectional data, meaning that they take a single snapshot of the patient's data at one time point instead of tracking disease progression. But liver disease is the dynamic process. It evolves day by day with lab values and symptoms changing rapidly. If the model does not include the time component, they miss the critical insights about when a patient's in the when a patient's in the most risk. Another challenges in completing the another challenges is incomplete or inconsistent data reporting. In some data sets, they are missing lab values, missing donor variables, or incomplete follow-up informations. And many studies does not clearly describe how they handled missing data or what pre-processing steps were taken, which makes it hard to reproduce or compare results. A big gap also exists in this inclusion of social determinant of health. Things like socioeconomic status, functional ability, access to care, or support system. These factors can dramatically influence both survival and recovery after transplantation, but they are rarely captured in traditional clinical databases. Additionally, a very few model users Additionally, there are very few model users that e- uh, sorry clinical real-time clinical database, but also they are also done in a single time and point. So while AI is promising, the data limitations are real barriers to developing robust, generalizable, and fair models for liver transplantations. So there is a need to overcome these limitations. So to overcome these limitations, we will need require collaborations and linking EHR data to improve data quality and including both clinical and non-clinical factors in future AI. Now also look at the modeling and methodological challenges that researchers face when applying machine learning to the liver transplantation. First, there is a current first there is currently no single best performing model for this area. Different studies have used methods like random forest, artificial neural networks, and XGBoost, but the results are inconsistent. What works well in on one dataset might perform poorly in other datasets, mainly because of variations in data quality, sample size, and pre-processing techniques. So there is no clear consensus yet which algorithm gives the most reliable predictions. Second, the one major issue is interpretability. Many deep learning models can produce highly and accurate predictions, but they act like a black box. We can't easily explain how or why these made a particular decision. In medicine, that is the serious problem because clinicians need to trust and understand the reason behind a model before they can use it for the patient care. So even if a deep models performs well statistically, limited interpretability often prevents its clinical adoptions. Then another challenges is a small sample size and imbalanced data sets. In liver transplantation, in liver transplantation, the number of available cases is very low, but the available cases is very low, and the outcomes like graft failure or patient deaths are often much rare than survival case. This imbalance can lead to model to overfit, meaning that they can learn the patterns on the majority class very well, but perform poorly on the minority outcomes that actually matters the most. Then also external validation is the another weak spot in this area. Many studies only performed an internal validation or cross validation using the same data sets they trained on, but this makes the model looks better on the paper but does not test how well they perform on completely on the independent data sets from the different hospitals or different populations. Without external validation, it's hard to know if the model is truly generalizable. Finally, there is a lack of transparency in how the models are developed. Many papers does not clearly describes which features were selected, how missing data were handled or imputed, and how potential biases were controlled. This lacks the methodological clarity, making it difficult to reproduce the results or compare models across studies. So even though machine learning holds a great promise for improving liver transplantation decision making, these methodological gaps need to be addressed before such models can be safely and confidentially used in the real world clinical settings. Now let's move to the conceptual and ethical limitation that exist in the current liver transplantation allocation model and AI systems. Even though AI and data science have made a greater progress, most of the current models, including meld-based features only, still mainly focusing on urgency. This means we are still prioritizing the sickest patient first without equally considering the utility or overall transplantation success. This creates an imbalance between saving the sickest person and ensuring the best long-term outcomes. There is also a major gap in models that can integrate both pre and post transplantation outcomes. Right now, we can predict who might die without transplantation, but we don't have reliable model that estimate total survival benefit. In other words, we can say that how many extra years or quality of life a transplant must provide. This is the biggest conceptual limitation is there. Another growing concern is algorithmic bias. When AI models are trained on the underrepresented certain groups, for example, a woman, minority population, or rural patients, those models can unintentionally learn and reinforce the disparities. Similarly, data from certain hospitals or geographic regions might dominate, leading to the institutional or regional bias. These demographic and geographic and institutional disparities are rarely examined in the current transplantation models. There is also lack of integration with implementation science, which means most AI models are tested retrospectively using the existing data, but not actually deployed or tested prospectively in real world settings. Without the real world validation, we doesn't know how well these models perform in day-to-day clinical practice. In terms of ethics, very few studies apply formal fairness or accountability frameworks. These things like transparency, explainability, and biases auditing are essential for reasonable AI use in medicine. Yet they are rarely part of transplantation modeling studies. Finally, this highlights the need for casual and explainable AI systems that don't just tell us what will happen, but also why that happened. If the clinicians can understand the reason behind the prediction, they much more likely to trust and adopt AI-based tools. In short, we can say that the goal is to make AI not just powerful, but also ethical, fair, and trustworthy in guiding organ allocation decisions. By considering this limitation, we have started work on the two projects. The first project is focusing on end-stage liver disease comorbidities in patients who are waiting for the liver transplantations. We know that many patients on the transplantation list doesn't just have liver disease. They also have other coexisting conditions or comorbidities like diabetes, cardiovascular disease, kidney disease, or obesity. These comorbidities can strongly influence both whether a patient is selected for a transplantation and how well they do afterwards, after transplantations. So the aim of this study is to identify and quantify these common comorbidities in liver transplant candidates. We want to understand how frequently do these conditions occurs and which one have the biggest impact on the patient outcome. Next, we plan to evaluate how these comorbidities affect post transplant survival, which for instance the one patients having diabetes or chronic kidney disease reduces the likelihood of long-term survival after a a liver transplantation. And we quantify the risk of data driven approach. We also want to bridge the evidence based guidelines, which means proven scientific plus clinical judgment with real world data. Right now the transplantation guidance gives us the general sense of which patients are highest risk, but they don't always match what we seen in the electronic healthcare data. So combining the EHR information with established clinical criteria, we can make those guidelines more accurate and reflective of accurate patient populations. Finally, the large goal is to build the foundation for personalized data-driven care. By using the machine learning and statistical models, we can develop predictive models that can help clinicians to tailor the transplantation decisions based on the individual's comorbidity profile, not just their only the MELD score. In short, we can say that this work move us towards a more precise understanding of how comorbidities shape the transplant outcomes and ultimately helps us personalized care for every liver transplantation candidates. Next, let's look at the overview of the study design of our project. We used a mixed method approach, meaning that we combined both exploratory and quantitative analysis to get more complete understanding of comorbidities in end-stage liver disease patients awaiting for transplantation. In phase 1, which is the exploratory phase, our goal was to identify the most frequent comorbidities seen in the liver transplant candidates. This includes the conditions like diabetes, hypertension, then kidney disease and cardiovascular disease. We looked at how often these conditions appeared and how they might interact with one another. The step helped us establish the baseline understanding before moving to more advanced analysis. Then in phase 2, we moved into the quantitative analysis using real-world electronic healthcare data from 2011 to 2021. Specifically, we calculated a retrospective survival analysis, meaning we look back to the existing patients' records to see how different comorbidities influence the post-transplant survival over time. Our sample include 722 liver transplant patients from the University of Minnesota Clinical and Translational Science Institute database. This dataset provides rich longitudinal data including lab values, demographics, comorbidities, and transplantation outcomes, which allowed us to perform both descriptive and inferential analysis. For analysis, we started with descriptive statistics to summarize the patient characteristics, the prevalence of each comorbidities and patients and basic outcome measures. Then we applied Cox proportional hazard models, which is a statistical model used in survival analysis. This model helps us determine how each comorbidity affects the risk of death or graft failure over time, adjusting for one variables like age, sex, or MELD score. In short term, we can say that the design allows us to move from simply describing comorbidities to actually quantifying their impact on survival, helping us identify which factors are most critical to consider when prioritizing the liver transplantation candidates. In phase 1, our goal was exploratory, as I said earlier, to develop what we call evidence-based metrics for key comorbidities that commonly occur in patients with end-stage liver disease. We focused on 5 major comorbidities that have been repeatedly shown in the literature to impact liver transplantation outcomes. The first one is diabetes mellitus. That is, diabetes adds a significant metabolic burden to the body and associated with higher mortality both before and after transplantations, which meaning that managing blood glucose levels and insulin resistance become critical for those patients. Next is the chronic kidney disease. Many end-stage liver disease patients develop the chronic kidney disease. The CKD is particularly important because it affects post-transplant recovery. Patients with poor kidney functions before transplantation often have longer hospital stays and more complications afterwards. The third comorbidity is malnutrition, which is common but often under-recognized factor. These patients tend to have high frailty and poor resilience. Even though their MEL scores may not look high, their overall physical conditions can significantly impact surgical recovery and long-term outcomes. The fourth is portal hypertension, which serves as the major marker for the decompensations. When pressure increases, patients more likely to develop complications, right? Variceal bleeding, ascites, and hepatic. These signs that the liver is no longer compensating. And finally, we included ascites, which is the direct indicator for the severe end-stage liver disease progressions. Persistence ascites signals the disease and have advanced significantly, and that medical therapy is no longer sufficient, pushing patients to closure to needing transplantation. For each of these 5 comorbidities, we created a comprehensive matrices that includes their diagnostic criteria, then severity, staging, and common complications. These matrices are grounded in evidence-based practice, guiding and designing to help standardize how comorbidities are identified and classified across data sets. This idea is that by quantifying these conditions consistently, we can integrate them into the predictive modeling later, so that instead of just relying on the MEL scores, we also account for the broader health status of each patient. Now, let's move to the phase 2 of the work 1, which is the quantitative part of our study, where we analyzed real-world data from the liver transplant patients to understand how comorbidities impact outcomes. Our cohort include all adult patients, meaning those 18 years and older, who underwent their first-time liver transplantation between 2011 and 2021. We focused on first-time transplantation to maintain a clean data sets, but because repeat transplantation can have very different clinical trajectories. We also applied some exclusion criteria. We excluded patients who had missing and incomplete data. For example, those missing the date of transplantation or confirmation of mortality status, since those are critical for survival analysis. We also excluded the patients who had combined multi-organs such as liver or lung or heart transplantations, because those follow-ups are very different clinical courses. However, we did include the liver kidney transplantation case, since in many end-stage liver disease patients, kidney transplantation is performed therapeutically as a part of their management. In terms of data extraction, we pulled detailed information from the institutional electronic healthcare records. This includes, as I said earlier, demographics, laboratory values, comorbidities, and clinical encounters and mortality outcomes. All of this data was obtained from the University of Illinois clinical database, which provides the decade of worth of quality Patient level data. Our first sample size was 722 liver transplantation patients. The average age around 55 years and the standard deviation of 11 years, meaning that our cohort include both young and older adults. The group was predominantly male at about 68%, which aligns with the national trend showing high rates of liver transplant disease and transplantation in men. When we look at the post-transplantation outcomes, the mortality rates was 19.8% and the median follow-up period was approximately 1,500 days, which means roughly 4 years. The 5-year survival rate was about 80%, which is consistent with benchmark from other transplantation centers. Interestingly, we also found that youngest patients, those are under 48 years old, tend to have higher MEL scores, meaning they were clinically sicker and the time of clinical sicker at the time of transplantation, but despite that they had better overall survival outcomes comparing to older patients. This suggests that younger patients might be more resilient and recover better post transplantation even when presenting with more severe diseases. So overall, this cohort gives us strong foundation to study how comorbidities interact with demographic and clinical factors to influence survival after liver transplantations. Now let's look at the key predictor of the post liver transplantation mortality from analysis. We used Cox proportional hazard models, which helps identify which factors significantly influence the risk of death after transplantations. In this table, we can see several clinical and demographic variables along with their hazard ratios and p-values, which tells us about their statistical significance. Starting with the age at the transplantation, we found that age increases, the risk of the post-liver transplantation mortality also increases slightly. The hazard ratio is 1.02 and it is statistically significant with the p-value. This means that every 1 year increase in age, there is about 2% increase in the risk of death after transplantations. So, which means older patients tends to have poorer long-term outcomes compared to younger ones. Next, let's look at the waiting list time. Also showed a significant association with mortality with a very small but meaningful effect. The p-value also significance, which indicating that longer wait times before receiving a transplant slightly increases the mortality risk. This makes sense because the patients who remains on the waiting list longer may have more advanced disease or complications, but the time they receive their organ. Then we look at the delta MELD, which represents the changes in the MELD score while on the waiting list. Although it was not statistically significant at 0.05 level, the trend suggests that the patients whose MELD score was worsened more effectively over time tend to have higher post-transplantation risk. When we look at the comorbidities, diabetes mellitus listing stands out with hazard ratio of 1.56 and also significant. This means that diabetic patients had about 56% high risk of mortality after transplantations compared to non-diabetic patients. This aligns with what we know clinically. Diabetes contributes to the poorer wound healing, infection risk, and cardiovascular complications. Interestingly, the portal hypertension at listing also showed the productive trends with hazard ratio of 0.61. Though it is not statistically significant, but this may reflect the fact that portal hypertension itself is the marker of decompensation. But many of these patients are prioritized earlier and managed more aggressively, which could improve the outcomes. Then also we found that low albumin after listing was another strong predictor with hazard ratio of 1.73 and p-value of 0.03. That is also significant. Low albumin is a marker of malnutrition and frailty. both of which reduces the resilience after major surgery. So these patients are more vulnerable to post-operative complications and mortality. Finally, we can see that chronic kidney disease at stage 5 at the list of transplantation at the time of transplantation was also significantly associated with high mortality. Hazard ratio 1.75, p-value also significant. So, which means that end-stage kidney disease adds heavily metabolic burden and often requires dialysis, which can make post-transplant management more complex. So, to summarize this results, age, diabetes, low albumin, and kidney disease emerged as the strongest predictor for mortality after liver transplantations. These findings tells us evaluating comorbidities along with MEL scores provides the more complete picture of patient's risk and guide more personalized transplant decision making. This slide shows the Kaplan-Meier survival curve of our transplantation cohort. This Kaplan-Meier method is the standard way to estimate the survival probabilities over time, especially when the patients have different follow-up durations. Here you can see that the time points listed in days, 30 days, 90 days, up to 1825 days, which is roughly corresponding to 1 month to 5 years after liver transplantation. At the 30 days, there were 700 patients at the risk. We observed 18 deaths, resulting in the survival probability of 97.5%. This tells us almost all the patients survive the immediate post-operative period, which is consistent with the existing short-term outcome after liver transplantation. By 90 days, the survival was still high, 95.3%, indicate that early post-operative mortality remains low. At 1 year, the survival decreased slightly to 91.9%, meaning that roughly 9% of the patients had died within the first year after the transplantations. This is quite comparable to the national benchmark for the post-transplantation survival. At the year 2, the survival probability was 89.6%, showing the gradual decline in complications, infections, or graft-related issues accumulated over time. Finally, the 5 years, the survival probability was around 80% with the 95% confidence intervals. So, about 8 out of 10 patients are still alive 5 years after transplantation, which reflects the good long-term outcome for this cohort. You can also notice that gradual drop in the number of subjects at risk from 700 at the baseline and 268 at the 5 years because of the deaths and patients lost to follow-up. The standard error and confidence intervals remain narrow across all the points, indicating that the survival estimates are statistically reliable. Overall, we can say that this Kaplan-Meier results shows that short-term and reasonably good long-term survival among liver transplantation outcomes, with outcomes aligning well with national averages. This provides the reassurance about the quality of care and highlight the areas where we can focus on future modeling, particularly in predicting those patients who are at the high risk of decline after the first or second years. Now, let's discuss the interpretation of our findings and what they really mean in clinical context. From our analysis, we found that certain comorbidities, especially this chronic kidney disease at stage 5 and low serum albumin, are strong independent predictors for post-transplantation mortality. In simpler terms, we can say that patients who have severe kidney disease are poorer nutritional and protein status before transplantation are significantly higher risk of poor outcomes afterwards. This makes sense because both kidney failure and low albumin reflects the more advanced disease stage and reduce the body resilience to withstand a major surgery and recovery. Another important observation is that Timing of comorbidities onset matters. We have noticed that differences in the outcomes between the patients who are already had these comorbidities before they were listed for the transplantation versus who developed them later during the waiting list period. Patients who developed the new onset of comorbidities closer to the transplant often had the steeper clinical decline, which affects the survival more severely. So it's not just what comorbidities a patient has, but also when also when they occur, the influences risk. This highlights the importance of monitoring patients dynamically rather than relying on the single time point assessment. Finally, we can our findings also point out the limitation of current MEL3 model. The current MEL3 model is excellent in ranking patients based on urgency. It does not capture the full picture of the patient's health, and it misses the comorbidities, functional statuses, and nutritional markers and overall disease trajectory every time. In other words, MELS tells us the sickest patients liver is, but how the patient's liver is sickest, but not necessarily move towards under more. No, in other words, we can say that MELS tells us how sickest patient's liver is, but not necessarily the how the patient is sick in as a whole. This reinforces the need for move towards more comprehensive data-driven models, potentially use AI and machine learning that can incorporate these broader health indicators and better predict outcomes both before and after transplantations. And this is really where our research is heading next. Next, let's now discuss the strength and limitation of our first work. Starting with the strengths, one of the key advantage of this work is we combined evidence-based practice guidelines with longitudinal electronics healthcare record data. This means that we didn't just rely on the statistical trends on the registry data. We grounded our modeling in a clinically validated criteria, such as how comorbidities are actually defined and managed in practice. By integrating evidence-based practice framework with real-world electronic healthcare data, we were able to ensure that our findings are both data-driven and clinically meaningful. The second major strength is that our model was time-aware. Instead of treating comorbidities as a static factors, we looked at how they evolved over time, when they appeared, how long they persisted, and how the timing influenced post-transplant outcomes. This dynamic perspective is often missing in traditional MELD-based or registry-based studies, which tends as a single time point for analysis. Incorporating these time-aware variables is important in our analysis. Now, moving to the limitations with the more clinical data studies. With most clinical data studies, there are few important ones to note. First is that it was a single center cohort from the University of Minnesota database, which while the data quality is excellent, the findings may not be fully generalized to other institution or patients population with the different clinical practices or demographics. We had also missing data for certain variables, particularly related to malnutrition and albuminuria. These are the important predictors of frailty and metabolic health, but because of inconsistent documentation in EHR, we could not include them in all. We could not include all these variables for all the patients. So let's wrap up our work on. Let's go over the implication and conclusion of this work one study. Start with the clinical implications. One of the key takeaway is that the MELD scores, while very useful for ranking urgency, needs to evolve into the survival benefits based score system. Right now, the MELD preliminary focusing on short term mortality risk, who is most likely to die without transplantations. But what we really need is a system that balances both urgency and long term survival benefits. In other words, we can say that who is most likely to live with the longest and healthiest life after receiving a transplantations. The second implication is that comorbidity integration is absolutely essential for personalized predictions. Our findings clearly shows that factors like kidney disease, low albumin, and diabetes have major impact on outcomes. They not part of the MELD framework. Incorporating these comorbidities into prediction models would make organ allocation decision more accurate and individualized. The third implication is that AI-guided decision support system have a strong potential to improve both equity and efficiency in organ allocations. By combining these data from multiple sources, EHR lab values, and clinical notes, AI can help us to identify the hidden risk factors, reduce bias, and ensure the patients are prioritized fairly, regardless of gender. Now, moving to the conclusion, this study reinforces the end-stage liver disease comorbidities play a critical role in shaping the transplantation survival. They are not just secondary factors; they are central determinants of who does well after surgery. It is also emphasized that MELD 3.0 alone is not adequate for long-term predictions. While it performs well for short-term urgency, it does not fully represent the whole patients. It misses the impact of other organ systems and chronic conditions that influence the survival. Finally, the combined evidence-based practice guidelines and real-world EHR data, we can build the next generation personalized liver transplantation care. This approach allows us to move beyond one size fit all scoring system towards modeling that adapt to each patient's clinical complexity and dynamic risk profiles. Now let's move into the work 2. The work 2 focusing on using the machine learning for post liver transplantation survival predictions. Before we discuss the machine learning models, it is important to address some more limitations in the current MEL3 models, because that's what most transplantation decisions based on today. The MELD 3.0, we all know that the calculator score using the most recent laboratory results, including bilirubin, INR, creatinine, sodium, and albumin, and 6, to estimate the patient's probability of death within the 90 days while they are on the transplant waiting list. So it is an urgency based model that helps determining who is most at the risk of dying soon without transplantations. However, there are major limitations to this approach. The first is that the MEL3 only focusing on short-term survival. It does not tell us anything about long-term outcome after transplantations. In other words, we can say that it is designed to help decide who get liver first, but not who will actually benefit the most from receiving it. The second thing is the MELD just using the single snapshot of lab results. This is the important one. It looks the patient's most recent values right before the transplantations. But patients with end-stage liver disease often experience up and downs over time. Their bilirubin, sodium and creatinine levels might fluctuate depending on the treatment infection or complications. By considering the latest lab values, MEL 3.0 misses the longitudinal trajectory, how the patient's conditions have changed over time or over week or over month. The patients might have the same MEL score today, but one has been stable for 6 months, while the other has been rapidly deteriorating. Those are the very different risk profiles. It MELD 3.0 treats them as the identical. So the main takeaway is that limits the current MELD limits because it does not capture the disease progression or recovery patterns over time. It is it is like taking one photograph of moving object. You can get a still image, but you miss the story of the motion behind it. This is where ML allows us to use repeated lab measurements and longitudinal data from EHR to model how patients' health changes over time. By doing this, we can start predicting not just short-term risk, but also the long-term post-survival recovery and patient trajectories, which can make organ allocations more equitable and effective. This is the illustration of our study design that shows that overall workflow of how we build and evaluate our ML model for this post liver transplantation survival prediction. We start with the data from the University of Minnesota, then which includes the detailed electronic healthcare record data for liver transplantation patients from 2011 to 2021. From this database, we extracted all the patients who underwent liver transplantation during that period. The next step was data cleaning and pre-processing. This involves handling missing values, correcting data inconsistencies, and standardizing the laboratory values and clinical variables. Because this was real world electronic healthcare data, a large part of the efforts went into the ensuring the data quality and consistency across the patients and time points. After cleaning, we moved to the feature extraction and building, meaning that we created the variables that would serve as input for our model. These features include lab-based variables like bilirubin, creatinine, albumin, and as well as demographic and comorbidity information such as diabetes, kidney diseases, and age transplantations. We also derive time-dependent features, for example, how these lab values changes over time leading up to transplantations. Once the feature sets was ready, we did stratify data partitioning like 80 to 20% for training and testing. Then after testing that, after splitting the data, we implemented 3 machine learning models like Cox proportional hazard model, random survival forest, and XGBoost model. This is our overall study design. Next, we will see the work to study aim and data foundation for our study. The main aim of this work was to develop machine learning models that can predict long-term survival after liver transplantations. But instead of relying on the single MELD snapshot, we use temporal variation features. That is how patients' clinical parameters changes over time. We know that the liver diseases and recoveries are dynamic process. A patient's bilirubin and creatinine may fluctuate before and after transplantations. And those patterns can tell us a lot about prognosis. So rather than just taking one lab values before transplantation, we incorporate multiple time points to capture those longitudinal trends. This makes the model more sensitive to disease progression and recovery patterns. Next, we aim to capture their performance of the 3 modeling approaches. As I said earlier, Cox proportional hazard, random survival forest, and XGBoost. By comparing these 3, we could understand how traditional and machine learning models differ in their ability to predict long-term outcomes in liver transplantations. Then from the data source, we use de-identified electronic healthcare data from the, as I said earlier, University of Illinois, University of Minnesota, then it covering the 10 years period from 2011 to 2021. Our final cohorts include 716 adult liver transplant recipients. We exclude the pediatric patients under age 18 years of old and missing transplantation dates and informations. then combined organ transplantations except liver and kidney. Regarding the data extraction and cleaning, we focused on key laboratory measures relevant to liver and renal functions, including bilirubin, INR, creatinine, and sodium. Next, we also included white blood cells counts, hemoglobin, albumin. These biomarkers together reflect the liver transplantation in inflammation and nutritional status. We also performed the outlier removal to ensure the extreme or biological impossible values did not bias the model. We also applied backward imputations to fill the missing lab values by carrying the backward imputations to the nearest available variable for observations, then ensuring the temporal continuity. Finally, we maintained 30 days completeness windows, meaning that for every 30 period, we had a consistent record for lab values for analysis. Although this process produced the clean longitudinal data that was both clinically meaningful and computationally ready for ML models. The goal was to leverage these time series data to go beyond the static MEL framework and develop more dynamic and accurate survival predictions. Next, the slides explains how we extracted the features and how we selected the features and all. We mainly focusing on temporal variation of features, which means that we didn't just look at the one lab value at the single point in time, but rather than how those variables changes over time before the liver transplantations. For each laboratory markers like laboratory parameters, bilirubin, creatinine, and INR, sodium, albumin, hemoglobin, and WBC and platelets, we computed several statistical and time-based measurements. Finally, first we calculated the central tendency and dispersion metrics like mean, median, variance, range, then entropy we also extracted. Then we captured the temporal change indicators. We described the direction and magnitude of changes. Then first and last differences between those variables, then percentage change that gives the same difference as the relative portions, and the trends and the trend direction, which means the slope is the values are increasing or decreasing. Then we also added a measure of abnormality burden. This is the percentage of lab values that were outside of the normal clinical range. For example, if 60% of patients' sodium readings were abnormal, that tells us their condition was persistently unstable. This gives the good idea for disease burden and overall stress before transplantations. In addition to lab-derived features, we also include patient-level covariates like age at listing, uh, then waiting list time. We also included those factors. Finally, our outcome was time to event, meaning that we modeled the survival as the time from the transplantation until death or last follow-up. So this feature extraction steps allowed us to convert routine lab data into a set of rich time-dependent indicators for the patient health variability. This is what makes more model dynamic. It does not see patients' lab values at the one time point. It understands their entire trajectory leading up to the transplantation. This is the one example of temporal dynamics, basically how the lab values for the liver transplant patients fluctuates over time before the transplantations. Here you can see that each plot represents one key lab parameters. For example, bilirubin, creatinine, and INR and sodium, WBC, and hemoglobin all tracked across several years. The x-axis shows the date of lab collection, and y-axis shows the measured lab values at the time point. When we look at this graph, we can start to appreciate the story behind the numbers. For instance, you can see that Bilirubin and INR often fluctuate significantly. Both are direct indicator of liver functions, and those spikes usually represents the period of decompensation when the when the liver temporarily worsen. These conditions are up and downs are common in end stage liver disease. In contrast, something like sodium trends to say more stable but can show a downward trends when the disease becomes advanced, often reflecting the issues like fluid retention on and hypoanemia. Similarly, albumin levels usually shows the gradual decline over time, signaling a poor liver synthetic function and malnutrition. You will also notice creatine and WBC value shows occasionally peak. These might correspond to actual kidney stress or infection episodes. The hemoglobin, on the other hand, may drop due to anemia of chronic diseases or bleeding complications. What is really important here is that this gap demonstrated why we need temporal modeling. If we just take a single snapshot, says one bilirubin values before transplantations, we miss all the informations about how the patient's conditions evolved over time. A patient with stable lab values 1 year is very different from the one rapidly increases bilirubin or frequent spikes in INR. So this visualization captures the dynamic patterns, this trajectory of deterioration and recovery, which traditional Wells score doesn't include. By using these features, by considering these longitudinal changes, we can start predicting the outcomes more accurately. These plot shows why our study is focusing on temporal features, because health data is not statics. It tells a story over time, and understanding those trends is a key to building better, more personalized prediction models in transplantation survival. So in our study, we began extracting total of 54 features from the longitudinal laboratory data. These features capture the trends, aspects of how patient labs values changed over times, things like mean, median, variance, slope, and abnormality burden across markers such as bilirubin, creatinine, sodium, and albumin. To make sure our model focused on the most meaningful predictors, we performed feature selection using Pearson correlation analysis when two features were highly correlated. With highly correlated features above 0.8, we removed to avoid the redundancy, then left us with 34 independent temporal features. Each provided unique information about the patient's health and disease progressions. As I said earlier, next we split the data into 80 and 20. Then we also analyze some statistical analysis to see the difference between alive and dead patients using a Whitney U test for continuous variables and Pearson chi-square test for categorical variables. Then finally, we implemented this Cox proportional random survival forest model and XGBoost model to analyze the survival probabilities. This is the summary table for the Cox proportional hazard models, which serve as the baseline statistical approach for predicting post-transplantation survival. In this table, we can see that several predictors that was found to be significant, borderline significant or borderline significant in these models, each one representing a different aspect of patient's pre-transplant conditions. These shows the coefficients, hazard ratios, and confidence intervals, and the p-values, which helps us interpret the strength and limitation of these relationships. Let's start with the first one. The difference between the first and the last bilirubin levels. The coefficient is positive with a hazard ratio of 1.03. The p-value is significant, meaning it is statistically significant. In simple terms, we can say that every 1 point increase in the changes in the bilirubin over time, the risk of mortality after transplantation increases by about 3%. This tells us the patients whose bilirubin levels rises substantially before the transplantation, showing worsening the liver function. which means are higher risk of poor post-transplantation outcomes. Next, we have the percentage of abnormal bilirubin readings, which has the negative coefficients, and hazard ratio is slightly below 1. This suggests that higher proportion of time spent with the abnormal bilirubin values was associated with slightly lower risk. This means this may seem counterintuitive, but it could reflect the fact that patients with chronic but stable bilirubin elevations were better managed or had slower disease progressions compared to those with rapid fluctuations. Similarly, we can interpret all those metrics. So overall, what we learned from this table is that dynamic changes in the lab values, especially bilirubin and albumin, and patient factors like age and waiting list time are the strongest predictor for post-transplant survivals. These results highlight the importance of capturing non-static measures, but those values evolve over time. Next, this slide shows the comparison of the model with only the MEL score. Here, the coefficient is slightly negative and the hazard ratio is 0.09. The p-value is not significant. And we also got the less than 50 performance metrics for this MELD only model. Now, let's see the performance of all the models we have tested. The table compares how different models perform when predicting the long-term post survival using the two key metrics, the C index, which measures the predictive accuracy, and integrated Brier score, which measures the overall prediction errors. We can see that the random survival forest model achieves the best performance, and also you can notice that the MELD only models are underperforming with very low performance. So we can say that only MELD can't be a score for allocating the liver to give more survival for the patients after liver transplantation. This is the future. This is the future importance for random survival forest models. Here we can see that mean WBC and variance days since start, then waiting list time. These are the top 15 important features. Then this is the top features from the XGBoost gradient models. Then I would like to summarize the work two main motivation and key takeaways from our study. First, the current MELD-based model allocation system is preliminarily designed to predict short-term 90 days mortality for patients waiting for the transplantation. It does not tell us much about what happens after transplantations. So to address this gap, we developed the set of machine learning models, including Cox Question and XGBoost, that uses the temporal patient features. These features captures how a patient's lab values fluctuate over time, giving us more complete view of their disease progressions. Among these models, the random survival forest model performed the best. It discriminates the integration of Brier scores 0.151, showing the solid accuracy for survival predictions. In contrast, the model relied on only on the most recent MEL scores, performing poorly with C index values below 0.5. This clearly demonstrates that temporal patterns, how lab values changes over time, provide much stronger predictive powers than single snapshot based MELD values. So here the key takeaway is there is the need to incorporate longitudinal informations to the machine learning model, enhance survival predictions, and potentially improve the transplantation decision making beyond the current MELD systems. Then let's talk about the temporal variation features. We mean that why we need temporal variation features like mean variance, entropy, and first to last differences and percentage of abnormal lab readings. These features describe how patients' lab values changes over time rather than just looking at the single snapshot. They essentially reflect the dynamic death changes that happen in months leading up to the transplantations. For example, instead of only considering one bilirubin values before transplantations, we are capturing how the bilirubin fluctuates over time. And then whether it is steadily increasing or showing sudden spikes or stabilizing. This same approach is applied to other key markers like INR, albumin, and other key laboratory markers. The traditional models like MELD scores or MELD or simple regression methods miss these nonlinear patterns, but machine learning can detect them. By doing this, we can get the real-time picture of the whether the patient's conditions deteriorating, stabilizing, or improving while they are on the waiting list. That's major advantage because liver transplantation, the liver disease progression is rarely linear. Patients can worsen rapidly or temporarily recovering depending on many factors. Ultimately, including these temporal dynamics allows for more precise and individual survival predictions after the transplantations. It helps clinicians identify patients at high risk earlier and take the intervention or monitoring accordingly. This is the comparative model insights, starting with Cox proportional hazard models. This is a traditional statistical model that it has been widely used in survival analysis. One of its biggest strengths is interpretability. It produces the hazard ratios, which are very easily to interpret the clinicians and they can understand easily, and then they can communicate very well to the patients. For examples, we can directly say that how much variables like age or bilirubin increases the risk of mortality. However, it is the major limitation that it assumes the linear relationship and proportional hazards, meaning it does not handle non-linear or complex interactions well. Next, we will move to the random survival forest model. This model gives us the highest predictive accuracy in our study. It is a tree-based ensemble approach that performs very well with the noisy or imbalanced data. It's also robust to outliers. Then also, the random survival forest model can model nonlinear patterns and interactions automatically, which is why it's particularly good for the medical data that often does not follow simple linear trends. The trade-off is the random survival forest less interpretable than Cox proportional hazards. We can identify which variables are important overall, but not easily explain how they influences individual's risk. The same for the XGBoost as well. Despite the differences, it is interesting to note that all three models consistently identified the same top predictors, specifically waiting list time, bilirubin variations, and age. Consistently across different modeling methods strengthens our confidence that these variables are truly key factors in determining the post-transplant survival. This is the performance comparison with existing studies. The most existing studies utilize the registry data, but ours is real-time data. We got the highest C index of 0.71. This is the continuation of existing comparison with prior studies. The existing models mainly focusing on the static donor and recipient data. For example, things like donor age, cause of death, and recipient MELD scores, and often fixed pre-transplantation factors. These models were developed from large registries, mostly UNOS database, but they all share one key limitations. They rely on a single point. That means that every patient's health as static rather than dynamic, even though the reality even though in reality, patients' conditions often fluctuate while on the waiting list. So there is a need to consider temporal variation of the patients while those are in waiting list. Let's summarize the clinical and research implication of our second work. From the clinical standpoint, the main takeaway is that our model supports personalized organ allocation and early intervention planning instead of relying on static time point. Then instead of static time point, that means clinicians could make more informed decisions, for example identifying patients who might need closure monitoring and who could benefit most from timely transplantation. In terms of stability and framework, it does not limited to liver transplantation because it builds around the temporal EHR data and survival modeling. Then looking ahead, our future work will focus on explaining this framework in multi-institutional settings, incorporating comorbidity data and surgical details and validating its generalizability. The long-term vision is to integrate this into the decision support system that can assist transplantation teams in real time, promoting more equitable and efficient organ allocations. Then the next step is validation with multi-center EHR data. Then I will conclude my second work. To conclude this part, the key message is that traditional post-transplant survival models can several important limitations. Most existing rely on static recipients or surgical variables, meaning that they use only time point data such as lab values or MEL scores before transplantations. This makes it difficult for those models to capture how patients' condition changes over time, and that is critical gap while we are trying to predict long-term outcomes after liver transplantations. In our study, we addressed this by including the temporal variation features. This was derived from longitudinal lab data. So instead of just looking at the most recent values, we considered each lab parameters like bilirubin and all the lab values fluctuating over time while the patients was on the waiting list. This allows the model to reflect the dynamic status of each individuals rather than static snapshots. When we analyze these features using random survival forest model, we found that significantly outperformed MELD and previous models, achieving the C-index of 0.71 for predicting long-term post-transplantation survival. This substantial improvement and shows the value of using the time-based informations. Then continue this work. We are working on predicting the length of stay for the liver transplantation patients, then predicting feature MEL scores of those patients, those who are in waiting list. Then also we are in the process of developing a next generation MELD framework by designing the AI and ML models using patient comorbidity and all the lab values and temporal variations. We mainly focusing on survival benefit model towards a survival benefits based allocation system for the organ allocation. This is my references. Then I would like to end by acknowledging the people and the organization who supported this work. This project was funded by University of Minnesota CTSI through the NIH grant. I also want to thank my collaborators, Dr. Lizani Prunulli and other collaborators for their valuable help with data analysis and model development. And I would like to thank the University of Minnesota and the University of Florida for their institutional support. This work truly reflects the strong team efforts across different disciplines. Then I would like to thank you all for your time and attention. I really appreciate the opportunity to share our work with you all today. Yeah, that's all I have. Actually, I took a lot of time for presenting this. So many informations I need to present, but it's time constraints. If you have any questions, kindly reach out to me to this email ID. I can happy to answer your questions.
Participants, if you have any doubts, you can post in the chat box or you can email it to ma'am.
Yeah, I have another meetings. I need to move to
Oh,
that. So if you
okay.
guys any questions, please email me. I'm happy to answer all the questions. Kindly share the feedback with me, ma'am. Jennifer, ma'am.
Sure, ma'am. I'll share it with you. Thank you, ma'am, for your enlightening and inspiring session. We deeply appreciate the time and effort you took to share your valuable expertise with us. Thank you so much, ma'am. That was a very wonderful and informative session for all the researchers.
Thank you, ma'am. Thank you for this opportunity to present my work. Yeah.
Thank you, ma'am.
I think still people keep on coming inside, so I got distracted somewhere.
Yeah, maybe because of poor network connection, they leave, they get disconnected and they
Yeah.
join again.
Yep. Yeah.
Uh,
Okay, ma'am. Thank you.
Hello.
I have to leave. Yes, ma'am.
Thank-
Someone is
So,
asking.
yeah, hello, hi, ma'am. I have a
Hi.
question.
Yeah, ma'am. Go
Hello.
ahead.
Yeah, this is
Yeah, ma'am.
Aisha. I'm from Mangalore. So I'm a research scholar. Basically, I'm working on biomedical computer science. I'm into computer science, AML. But in collaboration with radiology, I'm just started my PhD. So it's basically regarding the image fusion and attenuation correction and so from PET images. So
Okay.
any input that I can get regarding the attenuation correction, like because I just want to know there are many methods like DICOM methods and Atlas based and MR based, and then comes the DL based. So how can I proceed with this? Like, what exactly can I start with?
Actually, you are asking the questions to the wrong person. I am not the image analysis person.
Okay.
So I am not help you with the answer for this.
No, is this attenuation correction something it got to do with signals? Something there we could work on it?